Hello, in this video I'm going to take you through the enthalpy of combustion subtopic in Unit 3 of the Higher Chemistry course. So the purposes of this video is to teach you the definition of enthalpy of combustion and show you how to calculate the enthalpy of combustion of a substance through experimentation. If you see a little pen icon at the top of the video, you probably want to pause it and note down what it says if you are learning this for the first time. So first of all, what is enthalpy of combustion? So there's a standard definition for this that you need to learn. So the definition of enthalpy of combustion is the energy released when 1 mole of a substance burns completely in oxygen. So is basically the energy that's released in a complete combustion reaction. Okay, so things to remember are the general equation for complete combustion. If you have a hydrocarbon and it burns in oxygen, so all combustion reactions require oxygen, and that burns to produce carbon dioxide and water for a complete combustion reaction. You can also get incomplete combustion, where you don't make carbon dioxide, you only make carbon monoxide because you have a limited supply of oxygen, and you would also produce carbon soot, which is like a black solid material. So if I give you a specific example of enthalpy of combustion equation, so if we go with methane, CH4, plus O2, giving you CO2 and H2O. So if we balance that, the carbons are already balanced, that's fine. The hydrogens, we need to multiply this by 2, so there's 4 on each side. And then for the oxygens, we've got 4, 1, 2, 3, 4 on the right, so we need to put a 2 in front of here. The important thing when you're writing an equation for enthalpy of combustion is that you only have 1 mole of the substance you're burning. So 1 mole of the substance being burned. Okay, because there's a 1 mole in the definition. Right, so it doesn't matter how many moles of oxygen you require or how many moles of carbon dioxide and water you produce, it all comes down to the fact that you're just burning 1 mole of the substance. So do another one as an example. So let's do ethanol. So that's C2H5OH reacting with oxygen to give you carbon dioxide and water. So now we need 2 carbons on the right, so put 2 there. The hydrogens, we've got 6 on the left altogether, 5 plus that one in the hydroxyl, so then we need 3 moles of water. So then if we do the oxygens last, we've got 4 and 7. But you want to remember there's an oxygen in the alcohol, so we actually need 6 from the O2s, because if we get 6 from the O2, then the 7th oxygen we need to be made up from the ethanol, so 6. Okay, but again, we still only have 1 mole of the substance being burned. That's the important bit about the enthalpy of combustion. So you want to make sure that you remember this definition, and you may be asked to write an equation for the complete combustion of a substance. So if that's the case, you're just reacting it with oxygen and it produces carbon dioxide and water, and then you balance it. So how the experiment works, if you've done National 5 chemistry, you'll have seen this experiment before, where we've got a metal container containing water, usually, that we heat using our fuel for a set period of time, and we measure the temperature of the water before and after so that we can calculate how much heat energy is being transferred into the water from our fuel. So that's how it's done at National 5. In higher, in order to calculate the enthalpy of combustion, we need to know how much fuel we've used. So just having the time, like having a set time of burning isn't sufficient for calculating enthalpy of combustion. You need to know how much of the fuel you've actually burned. So it's basically this, it is the exact same experimental setup of the equipment. So you've got a known mass of water, you've got a clamp stand with your metal beaker. Remember, you use a metal or copper can as the beaker because it's a better conductor of heat, so you'll get better heat transfer into the water. You use the draft shield around the outside to try and minimise the heat loss to the surroundings. And you've got your spirit burner underneath, and you want to make sure the flame isn't too far away from the copper can. The other thing with the thermometer, you don't want the thermometer touching the metal, the copper can, because that would give you an inaccurate temperature reading, because it's most likely the copper can is going to be hotter on the surface than the water would be. So you ideally want to take the temperatures from the middle of your water. So before you start the experiment in this occasion, because you need to know how much fuel you've burned, you need to weigh the spirit burner first with your fuel in it. Then you also need to record the initial temperature of the water, which you would have done in National 5 if you'd done it. And then again, you burn the fuel for a set amount of time, and then record the final temperature of water and re-weigh the spirit burner at the end. Okay, so you weigh the spirit burner before and after and take the temperature before and after. Then you would repeat the experiment to get an average, because that's what we like to do in science. So once you'd carried out the experiment, you would end up with some raw results that look like this. So you've got your initial and final temperature of the water, and your initial and final mass of the spirit burner. So from that, in order to do the calculation for the enthalpy of combustion, we then need to work out the temperature change and also the mass of ethanol that was actually burned. So the temperature change, you're just taking away the initial and the final temperatures. So that would be 21 for experiment 1, and for experiment 2 it would be 22. So then for the mass of ethanol burned, again, you would just be taking them away. So what, 12.5 minus 11.53 for the first one. So that's 0.97 grams. And then for the second experiment, 11.53 take away 10.6 is 0.93 grams. So then we calculate the average changes. So the average temperature change would be 21.5 degrees, and the average mass of ethanol burned would be 0.97 plus 0.93 divided by 2. If you're doing this on your phone as a calculator, don't forget to press equals after you add them before you divide. Otherwise, you just divide the last number you typed in by 2. Your calculation will be wrong. It's a bit annoying. So once you've got your average temperature change and your average mass of ethanol burned, you're now ready to actually start the calculation. So first thing you need to do is use EH equals CM delta T. So if you've done National 5 again, you have used this equation before. So use this first to work out how much energy was actually released when we burned our ethanol for 2 minutes. So C is 4.18. It's always 4.18. If you do physics, you might know it as 4,180 something in joules. So in chemistry we use it in kilojoules, so just bear that in mind. It is in the back of your higher chemistry data booklet anyway. The mass of water. So the mass of water we had was in the picture on the previous slide, which was 100 centimetres cubed of water. So if I write this up here, so we had 100 centimetres cubed of water. Each centimetre cubed of water weighs 1 gram, so that's equivalent to 100 grams. But you must remember to change the mass into kilograms, because the specific heat capacity of water is in per kilogram. So that would then be 0.1 kilograms, and that's the number you want to put in for the mass of water. Don't let the mass of the fuel confuse you, because you will be given that in a question, but you don't need that until the second stage of the calculation. So you, for EH equals CM delta T, you only care about the mass of water. Okay, so put the mass of water in kilograms, and then our change in temperature, we're going with our average, so that'd be 21.5. So Put that in my calculator. That comes out as 8.987 kilojoules. Okay, so that's how much energy we got from the experiment. But that's not actually the enthalpy of combustion, because the enthalpy of combustion is the energy you get from 1 mole, burning 1 mole. So energy released from burning 1 mole. So this is what we're trying to work out now. We got this much energy from burning this much ethanol. So what we're going to do is set up a directly proportional relationship to say that 0.95 grams of ethanol gave us 8.987 kilojoules of energy. Okay. Then we find out how much 1 gram of ethanol would have given us. So that would be 8.987 over 0.95. Okay. If the decimal confuses you, and because a lot of people feel that they always need to multiply by a decimal, imagine that was a whole number. So imagine that was 95 grams. You would be dividing by 95. So it's the same thing when it's 0.95. And then we need to multiply up to the mass of whatever the mass of 1 mole of ethanol is. So ethanol is C2H5OH. So the gram formula mass of that is 2 times 12 for the carbon. Altogether we've got 6 hydrogens and then the 1 oxygen. So that would be 24, 6 and 16. So if you add all that together, 24 plus 6 plus 16, I'm using my calculator because it's currently 9 o'clock and that's too early for mental maths for me. So 46 grams. So we need to scale up to 46. You can't even write numbers at 9 o'clock. So that would be 8.987 over 0.95 times by 46. I always leave it till the end before I type it in my calculator because it just gives you better results from, you don't lose accuracy to rounding. Times 46. So that comes out as 435.01. If you want to, you can just have it as 435. Now the enthalpy of combustion, because it's energy released when you burn 1 mole, the units are kilojoules per mole. Okay, and because combustion is an exothermic reaction, so you're releasing the energy, it's always got a negative in front of it. Okay, so the enthalpy of combustion from this reaction of ethanol is negative 435 kilojoules per mole. So that means if you were to burn 1 mole or 46 grams of ethanol, you should get that much energy out. Okay? So if we go on to the next slide, we've got some more worked examples here. So I'm going to take you through this worked example, and then there's a few for you to try for yourself with answers to follow. So we've got a mass of fuel. Remember, you don't need that for AH equals C of delta T, so don't let that confuse you. And then we've got a mass of water, and then some temperatures. So we start off with AH equals C and delta T. So the specific heat capacity of water, which is C, is always 4.188, times by the mass of water. So that would be 0.1 kilograms if you divide it by 1,000. And the change in temperature would be 7 degrees. It's 2017 by 20. So I can do that much mental maths at 9 o'clock in the morning. So if I type that into my calculator, that comes out as 2.926 kilojoules. Okay, so that's how much energy we got when we burned 0.3 grams of methane. So 0.3 grams of methane gave us 2.926 kilojoules. 1 gram would give us 2.926 over 0.3. And 1 mole of methane weighs 12.416. So we want to find out how much we would get if we have 16 grams. So 2.926 over 0.3 times 16. And if we type all that in, that comes out as 156.1 kilojoules per mole. Again, you can round it to 156 if you want, and it's an exothermic reaction, so it gets a negative symbol in front of it. Okay. So next we have the questions for you to try, so you can pause the video as required to try them. I'm just going to flick through them just now. Okay, and there's the answers. You can check if you got them right. Hopefully I did. So what we're going to talk about now is something that, I know, I bet you thought that was the end of the video. Unlucky. So if we were to compare some of the results to the values that you get in the data booklet, we would probably find that our experimental values were a lot lower. So if we go back, for the first question, which was for the enthalpy of combustion of methane, it was 120.4 kilojoules per mole, say. In the data booklet, it's 891, so our experimental result is a lot lower. The reason for this is because we've got two problems with our experiment in the lab. So we've got a setup that allows heat to be lost to the surroundings. So even though you've got your draft shield, you're probably still going to end up losing heat to the surroundings. It's just almost impossible to avoid with that particular experimental setup. The other problem we have is that incomplete combustion could have taken place. So if there's not enough of an oxygen supply getting to the fuel when it's burning, you'll not be getting complete combustion. So the fuel won't be burning completely, you'll be getting partially incomplete combustion, which doesn't release the same amount of energy. Incomplete combustion releases less energy than complete combustion does. So that's the two issues you have with this experiment. You may be sitting asking, well, how did the people that did the experiments for the data booklet get such good results? Well, because they used a special piece of equipment called a bomb calorimeter. Now, the bomb calorimeter is designed to maximize heat transfer into the water, because the water is what is telling us how much heat energy is being released. So it's not allowing any heat to be lost to the surroundings, and it's also preventing incomplete combustion taking place. So the two issues we have with the experimental setup that we would do in the classroom are negated in this particular apparatus setup. So I take you through the key parts of this. So the water is around the outside of the fuel. So your fuel goes in here and gets ignited. So it gets burned by these ignition wires. So it's just set on fire with electricity. So you don't need to open it to set your fuel on fire. So there's no heat being lost at all. It's totally encapsulated. And all of the heat will move out of this inner vessel into the water, so it's completely surrounded by water. So all of the heat is going to be transferred into there. You've also got a stirrer, which makes sure that the heat is evenly distributed around the water, so you're not going to be hot spots somewhere that could give you inaccurate temperature readings. And we've got this insulating jacket around the outside as well, so once the heat's transferred into the water, it should be kept there. As well as the insulated jacket, you've got a space of air, which air is a very good insulator also. So there's two layers of insulation there, which will keep the heat in the water. So that gets rid of the heat being lost to the surroundings issue. In this part here, and it's not actually labelled on, oh yes, here it is. So this is putting in pure oxygen. So there's 100% oxygen in this space. Okay, so natural air that you would be using to burn your fuel in the lab, in the classroom, has only got roughly 20% oxygen. in the bomb calorimeter, you're burning fuel in 100% oxygen, so there's no way that incomplete combustion is going to take place. Okay, so that's how the bomb calorimeter can give you much more accurate results, because it doesn't allow any heat to be lost to surroundings, and it also doesn't allow incomplete combustion to take place because you're burning fuel in pure oxygen. As far as its name goes, the name is a lot more exciting than the actual machine is. If you ever see one of these in real life, you actually can't see in the inside of it really, so it's actually really anticlimactic, and it doesn't make an explosion noise, if that's what you thought as well. Sorry to disappoint you. So that's the end of the video now, you'll be glad to know. So hopefully by the end of this you'll be able to state the definition of the enthalpy of combustion. You'll be able to calculate an enthalpy of combustion from a given set of experimental data, and you'll be able to state the 2 reasons that the enthalpy of combustion values in the data booklet are much higher than the ones that you would get from a lab experiment. Thank you very much.